Okay, okay, we're here to do 1988 Q2 from a previous AP test. A ball is thrown vertically downward, strikes a horizontal surface with a speed of 15 meters per second. It bounces, then reaches a maximum height of 5 meters, neglecting air resistance on the ball. What's the speed of the ball immediately after it rebounds? Okay, so let's sort of imagine what's happening here. It strikes the surface here at 15 meters per second, but it only bounces up. I shouldn't say only, but it bounces up 5 meters. So the first thing we got to think about is that this question implies some energy loss. Otherwise, there would be no point to the question, because part A, what is the speed of the ball immediately after it rebounds? Well, if there was no energy loss, you would just immediately put 15. That if it hits the ground with 15, it's going to bounce up at 15 unless there's an energy loss. So, excuse me, that must be some energy loss, and so the 5 meters high is not as high as it would typically bounce. So what's the speed after immediately it rebounds from the surface? Well, how fast does it have to bounce to get to 5 meters? So this is strictly a motion question so far. So we're going to start with VF squared equals VI squared plus 2AD. I already know that I'm going to go this equation because I have a bounce height, so I have D, I know A. I know that its velocity at the top of its bounce is 0, and I was looking for this. So it was kind of a no-brainer which equation I was going to use. And I'm looking for VI here. So VI is equal to the square root of VF squared minus 2AD. Well, the VF at the very, very top is 0. So really we're looking at minus 2. And my reference frame, gravity will be a negative. And the height is 5. So grabbing my handy dandy calculator, I'm going to be basically 9.8 times 10. I didn't even need a calculator for that. What's wrong with me? Take the square root of that. 9.9 meters per second. Okay. Easy peasy, lemon squeezy. Let's move on. So what fraction of the ball's initial kinetic energy is apparently lost during the bounce? All right. It's got to be a little tiny bit careful here, because if the initial velocity was 15 and it bounces up at 9.9, you may be tempted just to figure out the percent loss in terms of its velocity, but the question here is specifically kinetic energy, so we've got to do a quick calculation. So let's think about this in terms of kinetic energy before and compare it to the kinetic energy after the impact. The kinetic energy before, 1/2 mv, and this will be the 15 squared, and we're comparing that to the 1/2 mv, where this is 9.9 squared. So where this is this is the comparison we're making right here. Well, obviously these two terms have not changed. So really we're interested in the comparison between 15 squared versus 9.9 squared. So what fraction of its initial energy? That's going to be a percent loss type of a question. So the best way to do that is to take your, well, let's just figure it out. So we have 15 squared is 225. The 9.9 squared is not off the top of my head. 98.01. So what percentage difference is this? So what percentage was lost? Well, the amount that was lost was the difference between these two. So 225 minus 98.01. So 225 minus 98.01, 126.99. Now, what percentage of this, what percentage of the original 225 is this number right here? So let's just do a quick percentage. So 126.99 all over 225. Looks like 56.44%. So it lost 56.44% of its kinetic energy to the ground, to friction with the ground, vibrations when it hits the ground, heat. Just a side note that friction always causes heat. In fact, all energy eventually is dissipated as heat. So that kind of leads us into the next question. If the specific heat of the ball is 1,800 joules per kilogram degree Celsius, and if all that lost energy is absorbed by the molecules of the ball, which is slightly, it's kind of an assumption because obviously the floor would get some of the heat too. But for this question, it's saying assume that all the energy is going into the ball. How much, but does the temperature of the ball increase? So notice that this question, which appears to be a chemistry question, appears on a physics AP test. There's a couple reasons for this. One is specific heat is really about energy. And so, yeah, you do cover it in chemistry, but really it is about energy. And you could tell really with that variable, the joules right there. So you may have to rely sometimes on other knowledges or other information sets when you do an AP test for physics. In this case, even if you haven't taken chemistry, which I'm assuming you all have, even if you haven't, you should be able to look at this term right here and try to make sense of what the question's asking. Let's pretend you have no chemistry knowledge. I'll teach this as if you have none. The specific heat of the ball. Okay. It says that it's 1,800 joules per kilogram degree Celsius. So even with no chemistry knowledge, we should be able to figure out that, okay, that for every 1,800 joules of energy, that is going to raise the temperature of 1 kilogram of mass 1 degree Celsius. And you know that they're ones because there's always an invisible 1 here if you don't have these values, right? They're always just an invisible 1. So it takes 1,800 joules of energy to take 1 kilogram of mass of that particular substance to raise it 1 degree Celsius. Okay. So how much does the temperature of the ball increase? So the first question is how much kinetic energy has been lost, and then we can just quickly do this conversion. So how much kinetic energy has been lost? Well, it's similar to question B, but we're not interested in a percentage here. We're interested in an actual value. So let's take a look here. Okay. The amount of kinetic energy lost. Okay, so this is clearly just a continuation of the previous video. I didn't have to stop and think for like 3 or 4 minutes because I had a brain fart. That would be ridiculous and totally unprofessional and beneath me. So this is clearly not an edit to cover up that brain fart. We're solving part C as without any hesitation. And the specific heat of the ball is 1,800 joules per kilogram degree Celsius. A lesser AP physics teacher would pause for a moment and try to think about what was the mass of the ball, because the kinetic energy that is produced is definitely connected to the mass of the ball, right? So, again, a lesser person might have to pause and think for a moment, but instead, the way we want to think about this question is there's no mass given, so there must be no mass needed. We'll assume that the AP tests are written correctly, which is something I'm going to dispel on a later question because I have a typo that's significant. Anyways, the specific heat of the ball is 1,800 joules per kilogram degree Celsius. So for every kilogram of substance you have, you need an additional 1,800 joules to raise the temperature 1 degree Celsius. Notice that the degrees that this object will increase its temperature is proportional to the mass, and so is the kinetic energy. So what we're going to think about here is just this idea for a moment, that the amount of kinetic energy lost is really going to be this. This is kind of coming from above, right? So this would be your initial kinetic energy right here. This is your final kinetic energy here. So this is really the kinetic energy lost. And if we had that amount of joules, we could really just do a quick division here, like this, to figure out, you know, how many degrees. Like, for example, if the top was 1800 and the bottom is 1800, then we know that it would raise this object 1 degree. Now, what if the mass was 5? Well, then you could see that if this was a 5 and this was a 5, and now we would have to have a 5 in here, that those 5s would cancel. And so the mass is still actually irrelevant to this problem, because the mass is directly proportional, linearly proportional, because it's just m, to the kinetic energy. It is also linearly proportional to this specific heat. So the effect will be canceled out either way. So the way we're going to do this is to take advantage of that fact. And we've already figured out, really, this difference at the top right here. It was 225 minus 98.01, which is 126.9, essentially 127. Okay. Again, the halves are, they're proportional. The masses are proportional, linearly proportional. So this, and even if you wanted to, you could put an imaginary m on this term right here if you wanted to, and then just see that they'll cancel out at the end. So we'll take this 126.99 and divide it by the 1800 joules per kilogram degrees Celsius, and this would be joules on the top. And again, if you wanted to keep an imaginary m, you could have an m up there, and then this would cancel. That would, the imaginary m would have units of kilograms. Those would cancel, cancel, cancel. This goes on top, and you end up with a number of 0. I'm relying on. I have terrible 0.076, 0.7. Wow, 0.0706 degrees Celsius. Typically, you're not going to see a major increase in temperature when balls bounce. I mean, that makes perfect sense. It's not like balls get super, super hot when they bounce. But the loss of a kinetic energy into frictional energy does create heat, so the surfaces do warm up. So this is how you would solve C. You would take the amount of kinetic energy lost, which is right up here. And then if it takes 1800 joules to basically effectively increase the temperature of 1 kilogram by 1 degree, you would just simply do a division. If the top was 3600, then you would be 2 degrees, but it's not. It's only a very small number. So that's how you would solve C.